the Calculus and Analytic Geometry. So what I'm going to talk today, I'm going to talk on two problems from the exercise sheets, which some of you people are, maybe a majority of you people found difficult actually. So today's discussion is going to be the discussion on making sense of those two problems and solve them. So this is what that we're going to do today. So before getting into the statements of the problems and their potential solutions, I would like to recall some of the basic facts of the geometry that I'm going to actually use. So the fact number one that I'm going to use is that if you have, for example, a trapezium. So what is a trapezium? So the trapezium is a picture which has two sides parallel and two non-parallel actually. So the two sides are parallel and two sides are non-parallel. So let's say that the size of the smaller, what do you call, so these two lines are parallel, so the size of the smaller segment is A and the size of the bigger segment which are parallel to each other is B actually. And let's assume that this height, in other words distance between these two what do you call lines is h actually. Okay, the distance, the height of the trapezium is h. Now what is the formula for area of finding the trapezium actually? So probably you remember the formula, but we can pretty easily drive it actually. So yesterday talked about that how you can approximate the given pictures in the terms of the pictures, the given areas in the terms of the known areas actually. So for example, if I want to compute a formula for say the area of the trapezium, so what I can do is that I can split this trapezium into what you call two triangles actually. So now I have two triangles. So this is one triangle and this is another triangle actually. So this triangle has base B and this triangle has base what do you call A actually. While the height of the both triangles is h. So the height of this triangle is also h and the height of this triangle is also h actually. So I can say the area of this trapezium is really the sum of the areas of these two triangles actually. Okay. So what would be the area of this triangle, okay, which has base B and height say h? So we know that the area of say a triangle with the base B and height h is base multiplied by its height actually plus. So what would be the area of this triangle? So this triangle is going to be the 1/2 of the base, which is A, multiplied the height of this upper triangle, which is h as well actually. So if you simplify it a bit, so this is the formula for computing the area of the trapezium is going to be A plus B and divided by 2 times h actually. Okay, so this is fact number one that I'm going to use at some place actually while doing the solution. Let me talk about the fact number two. The fact number two is about what do you call the similar triangles actually. So imagine I have one triangle that has shape like this, and say I have another triangle that has shape like this actually. Okay, so so for example, let's give these names. So A, B, C, D, and E. Okay. So in the triangle, say A, if I say that okay, so these two triangles are, so the triangle ADE, so I'm going to say that triangle ADE is similar, okay, is similar to triangle ABC, triangle ABC, if and only if you compute the ratio of any two sides of one triangle, it's equal to the ratio of the other two sides. In other words, one triangle is really a zoomed version of what do you call the other triangle actually. So if, for example, in this triangle ABC, if I take this perpendicular and divide by, for example, base, so if I say that AC divided by BC, this must be equal to the perpendicular of this triangle divided by the base of the bigger triangle actually. So the perpendicular is, say, AE, okay, divided by what do you call DE actually, okay. And similarly, if you, for example, take, say, perpendicular divided by hypotenuse, it should be equal to the perpendicular divided by hypotenuse actually. So in other words, in one triangle, if you are zooming, then everything basically is zoomed in with a common, what do you call, factor actually, okay. So there is always a common factor, okay. So in other words, AC is something k times of, or maybe AE is k times of AC, and BC is k or the DE is the k times of BC. Similarly, this bigger hypotenuse of this bigger triangle is k times, in other words, this fixed number times the, what do you call, hypotenuse of the smaller triangle. So that's what really is the basics of the similar triangles actually. So this is also something that I'm gonna use, similar triangles. Another thing that I'm gonna use in one of the problems is really, what do you call, the law of cosines. I know that if you know, I have, say, a right angle triangle, and if, say, it is A and B and this is really C, then I know that there is a Pythagorean theorem that goes like A square plus B square plus equal to, what do you call, C square actually. So this is something that we all know. But the question is that instead of now having this 90 degree, imagine this angle is really more than 90 degrees. So this angle is, for example, theta. Okay? So this angle is some theta. Okay? It's more than 90 degree or less than 90 degree. The question is, then what would be the relationship between CAB? Interestingly, there is a law which is called the law of cosines. Okay? There is a law which is called the law of cosines, which says that if you have an angle, okay, let me make it a bit more clearly, that imagine I have this kind of triangle with the angle, say, theta, okay, and say this side is A and this side is B and this side is C. So in other words, we took the perpendicular of the right angle triangle and kind of tilted it actually. So now it's like it's more than 90 degree angle or less than 90 degree. So you can have an obtuse angle triangle or acute angle triangle, doesn't matter. Okay? Then the question is, will there be a relationship between C and B? The answer is that yes, there is going to be a relationship between the C and B. So C is the side that is opposite to the angle theta. So then the C square is really going to be like A square plus B square. Okay, so this is something that is common, what do you call, with Pythagorean theorem. So what I need to do is really to subtract 2AB cosine of the theta. Okay, 2AB cosine of the theta. So if this theta is 90 degree, okay, if this theta is 90 degree, then cos 90 degree becomes 0, and this term will go away, and you're going to get c square equal to a square plus b square. Okay, so this is also an elementary fact that you know from your FFE classes, and might be also from your pre-calculus class. So this is called the law of cosines. So similarly, you have law of sines, you also have law of tangents. So this is law of the cosines. So at one place I'm going to use law of cosines to solve the problem. The fourth and the final elementary fact that I'm going to use to solve the problem, one of the problem is really this factor actually, that if you have a circle, say of the radius, what do you call, r, okay, and so imagine this like as a stick actually, okay, and if I move this stick, okay, this radial stick with some angle, okay, so if I move this with some angle, so I took this stick and kind of rotated it with, say, angle theta, you can also treat it in that okay, you know, a particle has kind of moved from this location to this location actually. So the question is how much angle it made actually. So let's call this angle as, what do you call, theta. And this distance, you know, the distance between these 2 points, okay, you call this as the arc length actually. So this is the arc length of the circle, the arc of the circle, and you denote this distance by s actually, okay, this distance by s. Now you can immediately observe that this s is directly proportional to the theta. So in other words, the more bigger angle I'm gonna make, okay, the more bigger angle I'm gonna make, the more, you know, there is going to be the relationship between, the more, what do you call, bigger the arc length is going to be, okay. So this, what do you call, arc length is proportional to, what do you call, theta, while there is one thing that remains constant, that is radius actually. Okay, so this distance doesn't change in a given circle. So when you are moving around the circle, your radius would not change. If the radius is changing, probably you are not sitting on a circle actually. Okay, then s is going to be the r, which is kind of a constant of proportionality times theta. Okay, so what I'm going at one location I'm going to use basically this fact as well, that arc length of a circle is the radius time the angle subtended, okay, by that arc length actually, okay, or the subtended angle. So s equal to r theta. So these are the 4 facts that I'm going to use to what do you call, solve the problems. Now let's move to the problems. So the first problem that I'm going to solve is the problem what do you call, 28 from the list of I think it is the exercise 28 from the Calculus and Context James Stewart book, from the related rate problems actually, that okay, when you have 2 quantities related through a formula and your task is to find, what do you call, the relation of so if one rate is, so if you know that 2 quantities are related through a formula, and then their rates would also be related actually. And if you know one quantity, okay, then a rate of one quantity, you can compute the rate of the other quantity. So we went into the all details of that actually. So let's start with, for example, this problem 28 from the list, which actually talks about an interesting swimming pool. And this piece of information is given about the swimming pool actually, a swimming pool that looks like something like this actually, okay, so it looks like something like this, I think something like this, and this, and then this actually, okay, so we have a swimming pool, okay, the picture that is given in the problem goes like this, that you have a swimming pool that has what do you call, height at the deepest point, this total height, okay, so this height is really say 3 feet, I think, yes, it's 3 feet for this height of the chunk, and the height from this point to the deepest point in the swimming pool, the height is 6 feet. Okay, so the total height of, say, the swimming pool at the deepest point is 9 feet. Okay, so this net height is 9 feet of. Okay, this is what is one of the things that is given to me. Another thing that is given to me that is that the length of the entire swimming pool is 40 feet, and it's 40 feet in the following way. So the length of the entire swimming pool is the 40 feet, and it's 40 feet in the following way, that the length of this chunk, okay, is 6 feet. The length of this part is 6 feet. Okay, so this part is 6 feet long and 3 feet high. Okay, while the length of for the point from here to the point here, okay, so this length, okay, so this length is given to be 16 feet. Okay, so this is 16 feet, while this length, okay, which is the length of the deepest part, is what do you call 12 feet. Okay, this is also given, and the length of this part, okay, is really what do you call 6 feet actually. So this is 6 feet. This is 6 feet. So the net length, okay, so the total length of what do you call the swimming pool is 40 feet. So 6 plus 12, 18, 18 plus 6 is going to be 34, plus 16 is really 40 feet. Okay, so the height is total height is 9 feet, and total length is 40 feet. Okay, so the height is 9 feet to the deepest point, and the total what do you call the total length is 40 feet, and say for example the width that is given, okay, width of the swimming pool is fixed actually. So no matter what part you take, it has a 30 feet width actually. Here, here, here at L points. So the width of the pool is 30 feet. Okay, this is what is given. Now it says that imagine that this swimming pool is being filled actually. Okay, so it's being filled with the water. Okay, and it's being filled with the water, and the rate at which the water is being filled is 0.8 cubic feet per minute. Okay, so it is given that this, this is being filled, and the rate at which the water is being filled, okay, is really 0.8 cubic feet per minute. Actually, this is the value of if I call the volume of the entire swimming pool as say V, okay, so if V is representing the volume of the water that this swimming pool is holding, so V is say volume of water in swimming pool, okay, in pool, so this is the volume of the water, then the interpretation of this quantity is that this is the rate at which the volume of the water is increasing in the pool actually. So this is dv by dt actually. Okay, so this is dv by dt. So it's positive, so it's being increasing at what do you call this rate actually. So what else is given? Okay, what else is given? So what is the major question actually? So in this all situation, the major question kind of that we have to deal with is the question that how fast the water level is rising actually. Okay, how fast the water level is rising. How fast the water level is rising, okay, when it is 5 feet at, so in the entire swimming pool, okay, when it is given that it is 5 feet, it is 5 feet at, currently it's 5 feet at the deepest point at. Okay, so it is 5 feet at the deepest point. So this is all is really the statement of it. Let's quickly go through again. So we have a swimming pool which has a capacity to carry the what do you call volume. So there is a width and height, and so how we can compute, for example, volume of the entire swimming pool. So we need height, width, and what do you call length. So it is easy to compute. The capacity of the entire volume is, so this is 9 feet, okay, so it's 9 feet high, it's 40 feet long, and it's 30 feet width. So the total volume of this what do you call entire pool is really 9 multiplied by 40 multiplied by 30, okay. But there is a specific, so you have water level, now you are in, so this is the volume of the empty, what do you call, place, or you can say that this is the capacity of the swimming pool to hold the water actually. Okay, so I hope all this information is clear to you. Now let's imagine that the water level is at some location here actually now. Okay, so it's at an abstract location, what do you call here, and then the water is being poured, okay, through some source, and this water level is really, what do you call, rising actually. Okay, so what we have to do, we have to find that how fast this water level is rising actually. Okay, so in other words, if I say that h is the height of the water level, okay, so h of height of the water level, okay, then the major question is how this height of the water level is changing over the time. Okay, how this height of the water level is changing over the time actually. So we know the rate for the volume, we have to find the height for the volume. So the first basic task is going to be that what is the relationship between the volume, okay, of the water and say its height actually. So volume, the net volume of the water and the height of the water. So how they are related with each other, this is what is really going to be the first case actually. So what we can immediately see actually, that this picture, so you may assume that, you know, this is currently you have this much water in what you call the swimming pool, okay, and this is an arbitrary location, so it's not the location up till top. So let me make it a bit more clear that okay, so these 2 points are really right in front of each other. Okay, this is important. Okay, so this is what that we have to find. Now you can see immediately that currently the water is in the form of the trapezium actually. It's in the form of the trapezium. Okay, so now let's try to put the dimensions on the trapezium. By the way, I know that this is A, this is 12. So in a trapezium, it's like, okay, this is given to me, while this is unknown, okay, and the height is also what do you call unknown actually. Okay, so imagine that, okay, so if I, for example, break this down into 4 pieces, okay, let's call, say, this part A, so this length A, and this length, what do you call, B actually, this length B. And this is really the height h of the water, which is increasing actually. Okay, this is really the height of the water that is increasing. Now, say let's say this level, we have a lot of information about this level actually. Okay, so water has not reached up to this level. So this is important. Water has not reached up to what do you call this level. So on this level, so if I extend this line, okay, so if I extend these 2 lines, then I know that this is 6 feet, this is 12 feet, and this is 16 feet actually. So this information is given to me. Now I'm going to use 2 interesting what do you call factors. So let's now move to the volume of the formula actually. So the volume of the water, okay, the volume of the water is going to be the area of this cross section, in other words, area of this trapezium multiplied by the width actually. So the area of this trapezium, okay, this trapezium, okay, so you are seeing one cross section of the water actually. So the area of this trapezium multiplied by its width. So that would be the current volume of what do you call the water. So the area of cross section, which is not difficult to find, that this is really what do you call is a trapezium actually, which is a trapezium. Okay, trapezium times width. Okay, now in order to find the area of the trapezium, so what would be the area cross section of the area of the trapezium? So we know that if you have a trapezium and say the smaller side is A and the bigger, you have 2 parallel sides. So the small line has length A and this big line has length B, okay, and the height is h. Then the area of it is A plus B upon 2h actually. A plus B upon 2h. Now what is the length of the smaller side of the trapezium? So it is fixed, it's 12. Okay, so it's 12. What would be the length of this bigger side of the trapezium? So it's going to be A plus, since this is 12, so this is also 12 actually. Okay, so this is also 12. So this is A, 12 and B. Okay, B. So, and multiplied by height. So you're going to say this area of the cross section is going to be 1/2 times what do you call A plus 12 plus B, which is the size of the bigger line, and now add the size of the smaller line, which is plus 12 again. Okay, so this is going to be a plus b plus a plus 12 plus b plus 12. So that this is the length of the bigger side, while this is the length of the smaller side, multiplied by the width actually. Okay, so this is what it is. So the v is going to be the